All right, welcome to Unit 3, Chapter 16. We'll be talking about thermodynamics. So, what is thermodynamics? Well, we've already covered kinetics. Kinetics is how things happen, the movement of particles, individually or en masse. Thermodynamics is why things happen. Why do things proceed from reactants to products? Okay. Now, a lot of what we're going to be looking at finds its origin in the 19th century when scientists and engineers were trying to make better steam engines, trains. So the way they talked about things, the way they classified and understood things, was all about work and efficiency and energy and heat transfer within engines. And so that affects a lot of our vocabulary and the way we discuss things. But it's still very, very, very applicable to chemistry in various ways. So let's get right onto it. Enthalpy is half of thermodynamics. Just a nice quick review. Enthalpy is that delta H. Remember Hess's law, the enthalpy of a reaction, enthalpy of phase change, things like that. And at constant pressure, enthalpy is equal to the change in internal energy of a system is just equal to Q, the heat moving into or out of the system. And so that's one of the reasons we talk about enthalpy, because it's very, very useful for a significant chunk of chemistry. Constant pressure, that just means an open container, and just benchtop, desktop chemistry. It's the measure of the energy, or the change in the energy, I should say, of a system. And remember, everything wants to decrease its potential energy, no matter what kind of potential energy we're talking about. Whether that's, say, magnetic potential energy. Okay, when two magnets, pull closer together or push each other apart, they are minimizing their magnetic potential energy. Similarly, two charged particles, when they attract or repel one another, they are minimizing their potential energy. To bring two positively charged particles close together is to increase their potential energy. Okay, you have to do work to bring them together. Whereas you let them go, they fly apart like charges repel, and they do work moving away from one another. So everything wants to roll downhill, even if it's a conceptual hill, an electric hill instead of a hill made out of dirt. Okay? So when it comes to enthalpy, the release of heat from a system is a decrease in potential energy, and that is usually favorable. Well, that's always favorable. The problem is it's not the entire story. Now, continuing our review of enthalpy, we usually, not always, measure it through changes in temperature. Okay? So delta H, the change in enthalpy for a system, is equal to Q, the heat gained or lost by the system, is equal to Sm delta T. Sometimes S is written as C sub P. Either way, it just means the specific heat capacity. Okay? It's a property of the object. Okay? M is mass, and delta T is the change in temperature. Okay? So imagine you have this block. Say it's made of wood, could be made of iron, doesn't really matter. Say a block of iron. Okay? It's at a high temperature. It's sitting in some environment, just sitting on top of a table. And the air around is at a lower temperature. Okay? What's going to happen is that it's going to lose heat into the environment, and that heat is going to be equal to Sm delta T, where M is going to be the mass of this block of iron. Delta T is the difference between the hot temperature and the cold temperature. What did the temperature change of the block as it cools from its current high temperature down to the same temperature as the room it's sitting in. And of course, S is the specific heat capacity. Now, specific heat is a little bit more complicated. It's intrinsic to the material that the block is made of. Okay? So what kind of atoms or ions, whether it doesn't really matter if it's made of wood or iron or salt. Okay, whatever it's made of is going to determine its specific heat capacity, and how those atoms and ions and molecules and so on are put together. Okay, the internal structure, you know, the crystalline structure, if it's a crystal. These things all determine the specific heat of the material in question. So this mathematical formula, all told, should tell us nothing too surprising, right? A big object can hold more heat than a small object. Okay? A really, really big thing, you have to put in a lot of energy to warm it up. Or it's like the difference between heating up just 1 cup of water for a cup of coffee for yourself versus a heck of a lot of water for a pot of spaghetti, say. Okay? That just takes forever to get boiling. And of course, the bigger the temperature change, the more energy is moving in or out of the object. So those definitely shouldn't be too surprising. The heat capacity is a little bit more complicated, but it depends upon the material. Some materials are just better at storing energy. So, like for example, water has a very high heat capacity. It's very, very good at storing energy. It takes a lot of energy to change the temperature of water. Whereas, say, air is very, very bad at storing energy. It doesn't take much energy to heat up air at all. That's why on a really, really hot day, if the air isn't moving, if there's no breeze, you feel sweltering. It's because it takes like a half a nanosecond to heat up the air immediately surrounding your body to body temperature. And then that heat doesn't go anywhere because there's a good insulator. Whereas if there's even a slight breeze, then that's just incredibly refreshing because it's removing all the hot air from immediately around your body to replace it with slightly cooler air from elsewhere. So hopefully that'll help you understand, at the very least, how we measure enthalpy changes. So these are all things you have to measure, but that's one of the ways, not the only way, but that's one of the ways that we measure change in enthalpy. It's a nice and straightforward. You measure temperature change, you measure mass, the heat capacity, and you've got the change in energy of the system. Because remember, so long as it is at constant pressure, the change in heat is the change in energy. So we're looking at being able to measure very, very directly whether something is endothermic or exothermic. And remember, exothermic tends to be exothermic is favored, generally favored. Things want to lose energy. They want to get rid of that chemical potential energy. And the reason I keep on saying it tends to do something or it's favored is because you have to actually set the thing down and see if anything happens or not to know whether it's going to happen. So if you put a closed bottle of water on a table, what happens? Well, nothing. It's just going to sit there. It's closed, right? The water's not going anywhere. If it was coming out of the fridge, it might warm up. If it was full of hot water for some reason, it'll cool down. But nothing's going to happen, right? It's not really going to change. But if you put a closed bottle of ice on the table, well, then it's definitely going to warm up, and the ice is going to melt. Okay? There's a process that happens there. Now, you put a diamond on a table, what happens? Well, nothing, something. Diamond, that pure elemental carbon, it's what's known as an allotrope of carbon. It's one of the elemental forms of carbon. Diamond's actually unstable. Diamond is only the preferred form at very, very high temperatures and pressures. That's why diamond is only found in certain places where it comes rocketing up out of the Earth's mantle. The interior of the Earth is at very high temperatures and pressures. So eventually, you wait long enough, a diamond will turn into graphite, pencil lead, because graphite is the favored allotrope of carbon at normal temperatures and pressures. So we're talking about spontaneous processes. Okay? Water, changing to room temperature, whatever the temperature of the water is, that's a spontaneous process. You don't have to do anything, it'll just happen. Okay? You take ice out of the freezer, you put it on a warm tabletop, it's going to melt. That's a spontaneous process. You don't have to do anything to make that happen. Diamond changing into graphite, that is a spontaneous process. Okay? You don't have to do anything to diamond to make it change to graphite. It just will. It'll take an incredibly long time for graphite to change, or for diamond to change into graphite. Okay? It's a very slow process. But how fast something happens, that's you're talking about reaction rate, and that's a matter for kinetics, not thermodynamics. Okay? Thermodynamics tells us whether or not something will happen. Kinetics tells us how fast it'll happen. Okay? So that's what we're talking about with spontaneity, whether or not something is going to happen. So a spontaneous process is a process that will happen. You don't have to put energy in for a spontaneous process to happen. A spontaneous process, I shouldn't say that. You don't have to I want to be clear, but I also don't want to mislead you. You don't have to do anything special for a spontaneous process to happen. You might have to worry about activation energy, but everything has an activation energy, so that's not special. Okay, it might be a spontaneous endothermic system. I mean, that can happen, or a spontaneous endothermic process, I should say, and that can still happen, and that would require a source of energy from somewhere. But in general, you don't have to do anything special. Okay? You don't have to try to make a spontaneous process happen. Okay? Spontaneous process will happen all on its own. And the relationship between spontaneity and enthalpy is not direct and simple. Okay? Enthalpy helps us determine whether or not something is spontaneous. Many spontaneous processes are exothermic. Okay? Like I said, exothermic is favored, but it's not universal. Okay? But burning things, okay, that's an exothermic process. It's a spontaneous process. Okay? The unburned stuff is at high chemical potential energy. The burned stuff is at low chemical potential energy. So it wants to go from unburned to burned. Okay? It's a spontaneous process. Things rotting is also spontaneous. That is like burning, only really, really slow and stinky, and there's bugs. Okay? But enthalpy isn't the whole picture. Okay? Freezing is exothermic. Remember, going from liquid to a solid requires releasing energy. Okay? The liquid water is warmer than the frozen water, so going from liquid to solid requires a release of energy into the environment. It's an exothermic process. But not all water is frozen. There's a lot of liquid water everywhere, and that's a good thing for us. We require liquid water to live. Okay? So water melting is the exact opposite. Okay? Going from solid to liquid, that's an endothermic process. Okay? And yet, at above 0 degrees Celsius, melting is a spontaneous process. Okay? So at higher temperatures, water melts spontaneously. At lower temperatures, water freezes spontaneously. Okay? And yet, the process, regardless, freezing will always be exothermic. Melting will always be endothermic, regardless of temperature. Okay? So exothermic and endothermic, they're helpful, but they're not the whole story. We need something else. We need more information. And that is what we're going to get into beginning with Lecture 2.